Okay, well, how are we doing in general with life and class and homework? Um, I it was brought to my attention that maybe some of you are lacking the necessary R skills to complete the homeworks, and I'm looking around our classroom, but so I guess my encouragement would be to look through the presentations because all of the stuff that I have in the presentations are rendered in R Markdown, and that means the code runs exactly as you see printed and should run when you run it on your own computer. And so if you can look and understand the lines of code that I have written, then you should then be able to modify it to fit the needs that you need to do stuff. Okay. So on Monday, we looked at model diagnostics. Wednesday, we did our dplyr and tidy R tutorial. But we're going back to model diagnostics. And so this is all just tools to check the validity of our model. And so on Monday, we covered leverage and residual plots and standardized residual plots, as well as Cook's distance to estimate, the influence of a point to see if there are any certain points or outliers that might be causing trouble to your model. Okay, and model diagnostics is kind of it's a fuzzy part of statistics. It's not clean cut. Okay, statistics in general is not going to be clean cut because you're dealing with data from the real world, and rarely are things in the real world very clean cut and easy. Okay, so a lot of the data sets that we've been dealing with are nice and pretty and they fit these straight lines and stuff, but when you work in with real world data, it's not necessarily always like that. And the it says low battery here. So and when you do diagnostics, it might not be absolutely clear whether the model that you have is or is not a good fit. Okay. All right. So let's talk about what we'll cover today. So today we're going to have plots for checking their normality assumptions of errors and checking the assumption of constant variance. I left out the word of here. Okay, and then we're also going to look at transformations to possibly turn an invalid model into a valid one. And this will continue on into next week because there's a lot to say when it comes to transformations. And again, a lot of this is kind of just, there is some mathematical theory behind things, but then a lot of times you're just like, well, I can't even imagine what mathematical theory should be applied in this situation. And so there's kind of just a little bit of guessing and checking and feeling out what transformations might do the trick. Okay? Maybe I don't want to get in trouble for saying that, but I should probably say, always think of the appropriate mathematical model that would fit, but life's not always so pretty. Okay. So we've got the QQ normal plot of the standardized residuals. So we can take our standardized residuals, which should follow a normal distribution if our assumptions are true. Okay, and so one way to assess whether they are normal is through the QQ normal plot. Okay, so what does this say? So we look at the distribution of residuals and the normal plot. Okay, so the key thing is when you create your QQ normal plot, the dots of your residuals, okay, should look like a straight line. And again, the answer is not always clear cut as to whether things fit a straight line or not. Okay, so let's just take a look. So if you remember, do you guys remember the bonds, Treasury bonds model? Here, let's go back because it was Monday. That's ancient history. Let's see here. Okay, so this was our Treasury bonds model with we have what looks like a linear model, and then we've got these three outliers here. Okay, and this is the standardized residuals plot. Okay, and we want to see, you know, are these standardized residuals normally distributed? Okay, so ignore the spread this way, but just looking from the y side, and we were to create a histogram of the standardized residuals, could it be feasible that these are normally distributed? Okay, so let's just here actually let's see if we can actually do this. Okay, so let me just do a histogram of okay, so this is, you know, if I create a normal, just a histogram, this is our standardized residuals, this is what it looks like. You know, when you take away the fact that we're plotting them against the coupon rate, these outliers are no longer as apparent, right? So these ones have our values of close to 2 and 3, and they show up in our histogram out here. But if somebody says, is this normal or not normal, it's kind of hard to say just looking at this. And the QQ normal plot assists, but it you know, it's also, this is what it looks like. Okay, and the three dots that we have, those outliers, are actually out here, the values 2 and 3 and things like that. And then somebody has said, well, does the data fit a straight line? And you have to go, you know, I don't know if you're going to make that noise, but that's kind of the feeling that we have. We look at things and we're like, well, this might not be normal. So again, this is just one tool out of several. Okay, so the QQ normal plot in of itself is not going to answer questions. It might point to certain things, but it might not necessarily answer all of your questions either. Okay, so you know, when you look at this plot, it's very clear, you know, something funny is going on here. But just looking at the QQ norm of the residuals might not answer our questions either. Okay, when you have with the base graphics, you can do something called identify. So let's see. So I'm going to create our QQ normal plot here. And then you can say, well, I'm curious, you know, these ones stick out. I want to know what they are. Okay. And so to do this, you have to assign your QQ norm to an object. Okay. And then you say identify Q. And this only works with the base graphics thing. So you hit identify Q, and then you come over here and you notice your cursor has changed to like these crosshairs. And then you go, oh, I want this one. And then you click it, and then you say, oh, I want this one. And maybe I also want to know this one here. So you click those three, and then in tiny little text it says escape to finish. So then you hit escape on your keyboard, and it says, the points you selected were 4, 13, and 35. Okay, and sure enough, if we looked at our bonds model, the the bonds that were the flower bonds were 4, 13, and 35. Okay, so you know, it labels these as such, and so you can do that with identify QQ. Okay. Also, if once you've created your model, and if you just do plot the model that we have, bonds model, okay, it's going to show you a series of plots. Okay, so it says hit return to see the next plot, which in this case is our first plot. So this is residuals versus fitted. Okay, and we see, oh, these are the, you know, 13, 35. These are the weird ones. Notice these are residuals and not standardized residuals. So I think we talked about the difference between residuals and standardized residuals. So it is my personal opinion that this plot is not as useful if they had used standardized residuals instead. But it's not wrong per se. The second one is the QQ norm that shows up, and it automatically identifies what it considers maybe slightly unusual, 13 and 35 here. And then you hit it again, and it creates something called a scale location plot, which we'll talk about in a moment. And then and residuals versus leverage here, okay, which we see the Cook's distance. These are kind of like contour lines for Cook's distance, and we see plot 13, or item 13, has a Cook's distance over 1, which we said was significant, and this one had Cook's distance of over 0.5, which is pretty big, and we also see, you know, this one's pretty high Cook's distance as well. Anyway, just going back to creating our normal QQ, if you just say plot the model, and then you just say, I just want the second one, which is which equals 2, it creates this normal QQ. So you get the same thing as just plot the model, and this will be one of the plots that it produces. Okay, and then again, in conjunction with the other plots, you can kind of decide whether it was a good fit or not. So in this case, the QQ norm is not super telling as to whether our data fit, our residuals are normally distributed or not. Okay, you can also create it with ggplot, and to use ggplot, you have to run the command fortify on your bonds model, and then you would basically type out this command, and you say the sample you want is standardized residuals. Okay. And then here I'm adding the an AB line with intercept 0 and slope 1. This is optional, but if you want this line here, you would run that. Okay. All right, so I just wanted to briefly talk about how a QQ plot works, and we use the normal QQ plot most of the time, but you could have any probability distribution here. So you could have a uniform QQ plot, or a you know, beta QQ plot, or what do you do, Poisson? I don't know. You can pretty much any probability distribution you can create a QQ plot for. Okay, and so, you know, imagine our data set has the numbers 1 through 100. Okay, so 1, 2, 3, all the way up to 100. Is this going to be normally distributed? No, right? What's the distribution for the numbers 1 through 100? If I just uniform on the interval 1 through 100. Okay. And it says, so what we do is we take the values and we rank them from smallest to largest. And in our case, the value and the rank will be equal, but whatever, you know, values you have, you rank them from smallest to largest. Okay. And then based on the rank, with 100 numbers, you figure out, okay, I'm going to split up 100% into 100 little pieces, and then I'm going to find the midpoint for each of those pieces. Okay, so with 100 numbers, I picked 100 numbers because it's easy. Each one's going to go from, basically, will have a width of 1%, and I want to find the midpoint of that. Okay, so the midpoint of my first interval will be 0.005, half of 1%, right? And then the next one will be 1% away from that, 0.015, so on and so forth, all the way until the last one, which will have, the quantile will be 0.995. Okay. So far so good? Creating our thing. And then what we do is then we look up the z-score that would produce this quantile. Okay, and so if you look up negative 2.576 or whatever, you would see that you would get 0.005 in the tail. Okay, so basically based on, so these z-scores are based entirely on how many numbers we have. Okay, so if I had 50 numbers, then each quantile would be at, the first one would be at 1%, the next one would be at 3%, because each quantile, each unit would take up 2% of the chunk. So the first one would be at the midpoint, 1%, then 3%, then 5%, so on and so forth until we do it. So the z-scores that we have, the z-values are entirely determined by the number of data points that we have. Okay, and then what we do is we just plot the value against the z-score. Okay, and if these values are normally distributed, we would expect the smallest one to be approximately, the smallest being, the smallest out of 100, to be approximately, in line with our z-scores. And so if we did it for the values 1 through 100 and we create a QQ norm, we see for the theoretical quantities, which essentially are our z-scores, right? So our first one is negative 2.575, the next one is negative 2.17, and here is negative 1.96, essentially. We see those are plotted. This would be negative 2.57, negative 2.17, and negative 1.96, okay? And these are plotted just against the numbers 1 through 100. And so we see, if we plot them against 1 through 100, it doesn't look like a straight line, okay? And if I add the straight line, it should look like this, which says this data point out here should actually have a value. So here I scaled them to have a mean of 0 and standard deviation of 1. It says this data point should actually be down here, okay, around 2.5 standard deviations away from the mean. And these values up here should be at, way up here. So, if you think about the normal histogram and the uniform distribution, we see the middle ones, there's not enough in the middle, and then the ones out here, these values aren't far out enough to say that they are normally distributed. Okay? Is that all right? QQ norm, and then whatever other distribution, you would just find the quantiles and the corresponding beta score or whatever that would give what you want. Okay, so I just want to show you just some examples. So here I'm just taking random samples of 100, and we're going to see how closely do these fit a straight line. Okay, and the answer is sometimes closely and sometimes not that close, but these are all coming from a normal distribution. Okay, so I think one thing that will help you get better at spotting normal and not normal QQ plots is just looking at a whole bunch, looking at what is normal, what isn't normal, and then you can kind of get a better feeling of what these should be. So these are all normal data. Okay, so this is normal data. Does it fit the straight line perfectly? Not perfectly, but it is normal data. Okay, and so we've got all of these things. So these actually fit quite well. Again, not perfectly, and even something like this, it happens when it's random. Okay, sometimes you get values that are far out there. Okay. Over here, this is something that is from a t-distribution. Okay, so this is not normal. and from a t-distribution. And t-distribution looks similar to the normal distribution, but its tails are a little bit heavier. Do we detect that? In this one, I would say not really, but you know, if I ran this a few more times, okay, we might detect a heavier tail. Okay, so these are all, again, coming from a random t-distribution. Sometimes you get these, you know, flare-ups, but again, the t-distribution looks pretty close to the normal distribution, so it's hard to, it might not be always easy to detect, okay? We can do something where it's like very not normal, okay? Like the chi-squared distribution, and then we detect it quite readily. That you've got all of these data points way out here that shows a clear departure from the line that it should fit. Okay. Is that all right? Okay, so let's talk about assessing this notion of constant variance. Okay, so we can, we're going to look at a new data set here. This is, we're looking at hotel rooms, or at hotels, and we looked at how many cleaning crews they have and how many rooms they're able to clean. Okay, so we're expecting a relationship, you know, more cleaning crews you've got, more rooms you can clean. Okay, and so we create a model between, you know, let's explain the number of rooms cleaned based on the number of crews we have, and the data comes from this text file cleaning.txt. Okay, so so we plot it, and we see, yes, fewer cleaning crews. When you only have 2 of them, you can't clean that many rooms. When you have 16 crews, you can clean a bunch. But what do we also notice? It seems like the number of rooms, we don't have constant variance, okay? Meaning when you have a few number of cleaning crews, you might not be able to clean that many, but you know, the number of rooms you're going to clean is going to be within a tight range. You're not going to be varying from 0 to 50 rooms. It's going to be, you know, something between, you know, 10 and 18 rooms or something like that. Whereas with 16 cleaning crews, you've got a huge spread, because all 16, maybe they take a long time per room, so you can only clean a few. Maybe you've got, you know, the super rapid teams, and with that, it grows. And so we can kind of see that as we have more cleaning crews, you know, differences between speeds get, you know, grow a lot more as we get further out here. Okay, so just from looking at this plot, we can see non-constant variance. Okay, but in case it wasn't super obvious in a plot like this, we have diagnostic plots that will also help us identify non-constant variance. Okay. I think this is the exact same thing that I had. Okay, and this is the model summary that we have, but if you suspect that you have non-constant variance, we can't do inference with the model, okay? Because technically the model that we have is not valid, and anytime you have a not valid model, it is very dangerous to try to use this to make inference. Okay, so we have the model summary, but essentially I should say don't use this in its current state to make any kind of predictions. Okay. So so this falls under the tool of diagnostics to see if we have non-constant variance. So we can just look at the standardized residuals versus our x value versus the number of crews. And if we look at this, it seems very clear that we've got this funnel, this trumpet action going on here. Looking at the number of crews versus the standardized residuals, we see it seems to be growing that way. Okay, so this is just another indication that that things are not, we don't have constant variance here, okay? So yes, if you see the funnel, non-constant variance. We have other ways to diagnose non-constant variance. Okay, so why are we giving all of these tools? Again, it's just super important that your model is valid. Okay, and so if you should be running all of these diagnostics, and if anywhere along the way you suspect something might be wrong, that should be a flag like, okay, I've got to be cautious here. Okay, maybe you can't get a model that fits perfectly. No matter what you do, things don't seem quite right. Okay, but you still want to have a model. Well, there's kind of this old saying that says all models are wrong, but some are useful. Okay, and the truth is yeah, you're not going to be able to model things perfectly. Okay, because there's always just these things that we can't explain in life that are coming into play. So if you want to use your models for inference, then and it's not it doesn't seem 100% valid, just be very clear and transparent in your write-ups and say, I've done this and I've accounted for these things and I've tried to fix it. I'm still seeing some of this stuff. Okay, again, very important that our models are valid before we go on. Okay, so we have what we call the scale location plot. Okay, and this is one of the default plots that R produces when you just say plot the model. Okay, so you fit a linear model and you say plot the model. This is going to be the third plot that it produces. And what it is you plot the square root of the absolute values of the standardized residuals. Okay, so you take the standardized residuals, you take the absolute value of them, and you take the square root of those. Okay, what does this do? Okay, well, we'll see. All right, when you do this, taking the square root of the absolute value of the standardized residuals kind of helps take care of just a little, maybe some skewness that we might see in our residuals. Okay, and we plot this against x or we plot it against y. It really doesn't matter. So the default plots in R will plot them against I should say y hat, and it doesn't matter because x and y hat are linearly related, so it's just a matter of scaling on the bottom. Okay, so let's see what this looks like. Okay, so we can so you notice if I use ggplot, I'm taking the standardized residual, I'm taking the absolute value of it, and then I'm taking the square root of that. Okay, so this is what I have, and so this is our scale location plot for the cleaning data, and what we see is that the square root of the absolute values of the standardized residuals, this thing, what we see is that it increases as the number of crews increase, and that's a bad sign. Okay, ideally this line would be flat. If we have constant variance, we would expect this thing to remain flat or overall be flat. So this is what it is here. Here's just to contrast what a scale location plot looks like. I don't know why these pop-ups are showing up. Scale location plot looks like for a model with constant variance. So here I'm just making up some fake data where y is just double what x is plus some random variables, or just some random normal error. Okay, so this model has constant variance. Okay, I think it's very clear there. And the scale location plot for the model with constant variance is flat. Okay, so this is what the scale location plot looks like. And you can even, and this is like even going beyond, you can even perform linear regression between x and the square root of the absolute value of the standardized residuals. Okay, and then you can do see, is the slope that we see here statistically significant or not? Okay, and ideally, if we have constant variance, then the slope will not be significant. Okay, so so here is I fit a linear model between square root of the absolute value of the standardized residuals against x, and what we see is that the estimated slope is practically 0, and I've got a p-value of 0.8. Okay, so when you have constant variance in your model, you're going to have a flat line or something close to a flat line. You could perform a linear model between x and the square root of the standardized residuals to verify that it is indeed flat. Okay, this is again called the scale location plot. So if you just do plot of the model, okay, when you plot the model, this is the scale location plot. This would be the third plot that shows up, and what we see is an increasing slope. It fits it doesn't fit a linear model. It fits what's called a low-S regression line, which we'll talk about in a few weeks. Okay, but we see basically this curvature that says this is not so good. Okay, so this is with a heteroskedastic. Is just the long word to say non-constant variance. Okay, heteroskedasticity. Okay, constant variance. This is what our scale location plot looks like. Okay, so with the lowest line, it's not perfectly flat, but it looks pretty close to flat. Okay. And again, just as you look at more and more plots, your eyes will start to recognize, hey, this looks like there's a slope. This looks pretty flat. Okay. Okay, so we have a few ways to deal with non-constant variance or heteroskedasticity. Okay. Next week we'll learn weighted least squares, and this week and next week we'll learn transformations of the data. So you can take the log of your x values and the log of your y values, or you can take the square root of your x values and square root of your y values. There are guidelines that exist as to whether you should use the log transform or the square root transform, and it's based on the variance that you see in your model. But the truth is try a transform, see if that does the trick, and if it does, great. Okay, you can try the other transform and see if one model fits better than the other. Okay. And sometimes you do the transform and you're like, this isn't really any better, then keep the original model. Okay, so I know this is all kind of wishy-washy advice here, but sometimes that's how it goes. Okay, and so there is some mathematical reasoning behind doing a square root versus a log, but it's kind of fuzzy. It is fuzzy, especially when you're dealing with situations like, does it make sense to do this? Maybe not. Okay. So anyway, today we're just going to look at what transformations might fix this. Okay, and sometimes it can fix problems with non-constant variance. Okay, and then next week we'll look at how you can use transformations to estimate percentage effects rather than the regular slope. So the regular interpretation of the slope is when x goes up by 1, y goes up by this much. And then when you do the log transforms, it becomes when x changes by this percent, we expect y to change by this percentage. And then fixing problems with nonlinearity. Yes?
So when you say model to analyze it. So what are we trying to do?
Yeah, so transforms, maybe another word for transform is re-expressing our data. That might be a better word. And so what it does is you're basically just looking at the same data from another perspective, okay? Or just essentially you're changing the scale of the data that you're looking at. What this doesn't invalidate the conclusions. If you get a model fitting nicely, then the model is a good fit. It doesn't invalidate that. What it does, though, is it complicates the interpretations for your inference. Okay, so it's very easy. If we've got slope that says if the number of bedrooms in the house goes up by 1, I'm going to predict that the number of closets goes up by 1.6. That's an easy translation into real life. You can explain that to people, and people will understand. Okay, if you apply the log, okay, now things get weird, right? What does it mean to add 1 to the log of a number? It's a percent change. Now, so depending on what log base you have, adding something like 1 may translate into multiplying it by 10 or something like that, depending on what log base you have. And so I think for the natural log, adding 1 is multiplying it by whatever e is, and things like that. And so it gets weird, right? And so just once you fit your model and then you want to make inference and make conclusions from it, then you just have to kind of work backwards or forwards or whatever to make the appropriate translation. So we'll do that with just a very simple example here. But yeah, when you're switching from square roots or logs, it feels funny. That's all. Okay.
I'm just trying to improve your model.
Yeah, so when you have non-constant variance, okay, our model is not valid because one of these assumptions of our model is that the variance is constant throughout, okay? And so when you apply a transformation, now maybe you have constant variance when you're dealing with the square root of the variable rather than the actual variable. What does that even mean in real life? I don't know. It means if you think of the cleaning crews and the amount of rooms they clean, and you see constant variance with the square root, then it kind of shows that the cleaning crews, there's kind of like this like self-reinforcing thing that says, if the crew is slow, then having more slow crews, you're gonna end up getting low cleaning rooms and things like that. But here we'll take a look here. Okay. So with library dplyr, you can transform your data just using the mutate command here. Okay. So here, what I want to do is I want to take the crews and the rooms, and we're going to apply the square root to both of them. Okay. Can you just take the square root of one variable? You could. I think a lot of times if your x and y are dealing with similar units, then it makes sense to apply the same transformation to both x and y. So the book's recommendation is that in most cases, if you're going to apply a transformation, apply the same transformation to both x and y. And so in our case, we're dealing with counts for the crews, and we're dealing with counts for the rooms. So what I'm going to do is with dplyr, I'm going to take our current cleaning data set, and I'm going to throw it into mutate. And mutate is going to say, what we say is create a new column called square root x, create a new column called square root y. For square root x, what I want you to do is I want you to take the square root of the crews column. For square root y, I want you to take the square root of the rooms column. And we could name this whatever we want. I called it square root x and square root y, but if you wanted to call it crews SQ and rooms SQ, that's totally fine as well. Okay? And so we see, you know, when we do that, square root of 16 is 4, square root of 51 is 7.14. Okay? There are, I think there's a command in R called, I want to say transform, but I think the dplyr version is very straightforward in terms of how this works. Okay, so now that I have this, I can now fit a new linear model. So this will be the transformed cleaning model, and I'm just going to do linear model between square root y as explained by square root x, and data is coming from my cleaning table. Okay, and let's create the summary of this. Okay, and so we've got an intercept of this and all of this, and what does all of this mean? Okay, well, let's take a look. Okay, when we look at the data and the fitted line, this looks better. Okay, we don't really see the funnel action between square root x and square root y. We can take a look at the standardized residuals versus square root x, and we don't really see the funnel going on here either. Okay, so this is an indication that this model seems to be more correct in that we don't face the issue of non-constant variance. Okay, and the scale location plot, again, we have something that looks very much like a flat line. So this is all good. This is all good to say our data works. Okay, so let's talk about the inference that we can do based on this. Okay, so I'm going to create a prediction model, and my data frame that I'm going to create predictions for when x is equal to 2, 3, and 4. Okay, but keep in mind this is the square root of x equals 2, 3, and 4. So what was x, the original x? X is the number of crews I have. So here I'm now making predictions for having 4, 9, or 16 crews. Okay, so if I wanted to create a prediction for having, you know, how many rooms can I clean if I have 12 crews, then the number of rooms I would predict under 12 crews, I would have to do the square root of 12 here. Okay, and so the the fitted values that I'm the estimated for 2 is 4, and the estimated for these other numbers are here, and we also have lower and upper bounds for our prediction intervals. Okay, as we should. Okay, but again, this is now our y, but what is y? This is actually, we're making predictions for the square root of y based on the square root of x. So these are predictions for the square root of rooms cleaned. So if we want the actual rooms cleaned, we're going to have to take these values and square them all. Okay? If you did a log transform, you would then have to exponentiate to undo whatever it is that you have. Okay, so here we have to square these to get our predictions. So I'm just going to do p squared, and it goes element wise, so that's good. So what this says is if I had a cleaning crew of if I have 4 cleaning crews, then my best guess is we're gonna clean 16 rooms, but my prediction will be anywhere between basically 8 rooms and 27 rooms. Okay, if I have 9 cleaning crews, my best prediction is around 35, but I'm going to estimate anything between 22 and 50. And with 16 cleaning crews, my best guess is like 61, but I can guess anywhere between 43 and 82. Okay, and so when we apply the transform back to P, then we get our diverging predictions as well. Okay, and so applying transformations to X and Y is fine. It's just when you make the inferences back, you have to undo that transformation to get back into units that make sense. Otherwise, you'd be saying, the square root of X is related to the square root of Y, but nobody knows what that means, right? Like, if you have money, right? What's the square root of $1, right? As the number of hours goes up, as the square root of the number of hours goes up, the square root of money earned goes up by this. Our brains are not capable of thinking of what a square root dollar is. I have no idea what that is. But then, you have to undo the thing, and you get something like this, okay? And dealing with logs, now it becomes multiplication things, yeah.
So, like we're applying these transformations so that we can find like a model that fits the data we have currently.
Correct.
But then wouldn't that be prone to overfitting? Just because, like, if you're gonna force like a model to fit your data so well,
Yeah.
When even the linear model won't even fit the data. Right?
So I would say overfitting is more so a problem with including too many variables for your prediction. Okay? Over here, we're still basing it only on one variable, but we're creating a transform which allows for then in the non-transformed data to have a change in the amount of variance. Okay? So when we have something that looks like a funnel shape in the original data, by dealing with square roots or logs, it allows, it turns that funnel shape into something that has constant variance, okay? So, I guess the rule is, don't complicate your fit if you don't need to, right? Don't apply transforms unnecessarily. But if you're looking at your data or you're looking at your current fit and you notice this problem of non-constant variance, especially this funnel-shaped thing, then it might be worth considering a transform. And the transform may or it may not solve the problem that you're having. As always, your mileage may vary, and you, the researcher, has to make some judgment calls as to what should be done. And you could ask 3 different people and get 3 different answers on what should happen. And that's the messy part of statistics, okay? So, okay, well, happy Friday. We'll see you guys on Monday.